is the reason which guides your wave, is it? And which allows you you to pass through a wave, okay, with minimum energy loss. Okay, let's say you are having, think of the optical fiber, is it? That's actually a wave guide. Huh? That's a special case of the wave guide. Okay, so you allow let's say some electromagnetic signal to pass through the optical fiber, is it? So the loss is minimal, is it? So let's say if you are transporting, let's say, some energy across through the atmosphere, let's say it's open atmosphere, so that wave will get attenuated over a period of time, is it? So you want it to go through a certain direction, let's say from one point to the another point. Let's think of you are making a phone call in the old-fashioned way, I mean using the telephone, is it? So you are actually guiding the signal to pass through let's say through a definite wire, is it? So let's say you are having the TV cables, is it? So that's a kind of waveguide. You allow actually the signal to come, allow the signal to pass through that very wire, okay, with minimum loss, is it? Similarly, we can, it is not the waveguides for the only for the electromagnetic waves. We can have actually the waveguides for sound waves as well. Okay. So you are doing those kind of experiments with sound waves in your lab. Try to think of what is the waveguide there. Okay. So we will consider here a cylindrical waveguide, a cylindrical structure. Okay. It's very simple to do. Okay. Let's assume you are having a cylindrical waveguide. So it's of the infinite extent. Okay. So this is our cylinder. So we will allow an electromagnetic wave to pass through it. Okay. So and what is our actually motivation? We will see what are the allowed modes in this kind of structure. Okay, think. Okay, you have done this. That's a very good analogy. So you have done actually a particle in a box in quantum mechanics, is it? And let's say in one-dimensional view, what essentially you are calculating? You are calculating the energy in wave function. Okay, so these are the two things. So what you get from the wave function? You get actually what are the allowed values, allowed states in that very box. You cannot put a particle in the box arbitrarily, is it? You can put a particle in a given mode. It can be, let's say, in the ground state, first excited state, and so on, is it? You got my point. Let's say similarly, if you are having a particle in a three-dimensional box or any kind of potential, you always calculate what are the allowed modes or allowed energy states in that very case. Clear? Similarly, think of you are having an electromagnetic wave that is allowed to pass through this very, let's think of this box, okay? So what you need to calculate? So you will see what are the allowed wave, what are the possibilities, allowed modes, allowed energy states, okay? Through which I can pass, let's say, a signal through this very conductor or through this very tube. Think of an organ pipe. You know the organ pipe? So if you blow it arbitrarily, so what you will get? Huh? So let's say if you are having a simple pipe, you blow it, you will get nothing, is it? Okay, but if you look at the fundamental modes, so this organ pipe, you can have only different kinds of tunes and different kinds of modes, is it? So you figure out first, actually you can think that organ pipe as your what? A wave guide. You are guiding the waves through that very organ pipe. You can think that as a wave guide, okay? The sound waves are passing through and you are actually calculating what are the allowed modes. Okay, so you don't have any other possible mode, is it? Samajh? You got my point? So you can have only, you can design your tunes based on those allowed modes of the organ pipe, okay? Similarly, if you, in this very case, you figure out first the allowed modes and you see if you, for a given purpose, let's say what kind of signal you need to send through this very, let's say through this wave guide. So you will utilize those allowed modes, okay? Got my point? Okay, so let's think of the cylinder, it's of the infinite length, and let's say z axis. So you are having z, the axis of the cylinder lies along the z axis, okay? So this is the axis of the cylinder. So let me write now. So then you are having this xy plane. So let's write this as x and y. Okay, so in other words, the cross section of the cylinder lies in the xy plane. So this is completely arbitrary, this cross section, and it's actually closed curve, is it? Do you think it's a closed curve? Okay, it's a closed curve. Huh? So this cross section is a closed curve in xy plane. Okay, so now tell me, if I am having an electromagnetic wave passing through this, let's say, what is the direction of the propagation of the wave here? It is the z direction. Okay, so let's say if think of some wave, a monochromatic wave, let's assume. So what will be the profile of that very wave? So let's say if you are having a wave of frequency omega and wave vector k, and it flows across this very tube, is it? So it will flow along the z direction, is it? Is it true? So what will be the profile? So it will be simply e raised for I kz minus omega d. So this will be actually the time dependence of this very wave. Okay. So in other words, my wave, let's say this is, if I take, let's say, the electric field, it will be of this form. Okay. So if I take the magnetic field, it will be of this form. It will take the potential, because these are the solution of the wave equation, and the structure of the wave equation for E, D, A, phi, they are the same, is it? So they are the same kind of wave equations. So the same thing for A as well. So this kind of structure you can have. Any question? Got it? Okay. So remember this profile. So I will write. So the profile of the wave is simply, I will write it like this. Okay. So tell me, is omega same as c times k? So if you are having a wave flowing through this wave guide, so is omega same as ck? No. Because when you are having a wave passing through a medium, what will happen to the this k? So the speed will change, is it? So it will not flow through this, through this medium at the same velocity as c. Clear? So it will be lesser than c. Okay. So you should remember. We'll see actually. This is the dispersion relation. If omega is equal to ck, it is a dispersion relation in free space. In free space, electromagnetic waves travel at the velocity of light. Okay. But if it is not, so dispersion in medium is different. Okay. You can calculate. We'll see. From a dispersion relation, you can calculate what is the velocity of the propagation of a single wave and what is the velocity of propagation of a group of waves. That we call the group velocity. Okay. Clear? Okay. So let's move now. So let's go to the next one. Okay. So we are solving Maxwell's equation without source, since we have not considered. Okay, so one more point. So this cylinder I have considered as a conducting cylinder. Okay, so it's a conductor. Okay, a hollow conducting. So we are considering here hollow conducting cylinder. Hollow conducting cylinder. So you can consider other kinds of waveguides as well, but it is the simplest one. We'll do it. Huh? Okay. So let's. Have I considered any kind of source in my problem? So we have not considered any source. Okay. So that means we'll use the Maxwell's equation in free space. Okay. Okay. Since no sources are considered. So what is that? So first equation is del dot E is equal to 0, del cross E is equal to minus 1 by C partial B by partial T. Okay, then you are having this del dot B is equal to 0 and del cross B is equal to 1 by C partial B by partial T. Okay, so let's call this set of, okay. So now let's use that. So in these very equations, I want to remove this time dependence from these equations. So you don't have time dependence in this equation and this equation. So there is only time derivative here, is it? In this equation and this equation. And I know what is the time profile of the wave, is it? So since we are considering the wave moving along the z direction, its profile is that. So let's make the derivative of that. So B will be of the form, tell me. So you are having B, so that will be of the form of some B naught e raised for I k z minus omega t. Now tell me what is this partial B by partial t? So that will be minus I omega, the same thing B naught e raised for I k z minus omega t. In other words, that is same as minus I omega vector p. Clear? Got it? So in other words, so we are using, so let's call this as first term. So call this profile as first term, what I have already written. So using equation first, we get, so you are having this del dot E, it's equal to 0, del dot B is equal to 0, they are the same thing, and del cross E, okay, so that's equal to I omega by C vector B, and del cross B is equal to minus I omega C vector. So let's call these equations as equation second. So keep track of these equations, okay? Got it? So let's define these objects. Okay. So let me write nebula perpendicular. Okay, let's write that means, so it's this kind of object, it contains only xy, partial by partial y. Okay, so which implies therefore this nebula is equal to simply nebula perpendicular and partial by partial z. Clear? Everybody is following it? What I am doing, I am actually separating out the transverse direction and the longitudinal direction. For transverse direction, I have put as a perpendicular. Okay, what are the transverse directions here? X and y axis, is it clear? Okay, so similarly I can write this E as, so let's write this E as E perpendicular and EZ. So what is E perpendicular? So B is equal to B perpendicular B Z. So what is E perpendicular? So that is the components in the xy plane. And what is B perpendicular? So these are simply definitions. Bx. Okay. So these are the definitions. This is simply the notation. Okay. Let's rewrite equation, set of equations 2 in this kind of notation. Okay. So that means we are separating out the transverse components and longitudinal components. Clear? Okay, so let's do it. Okay, so let's take this del dot E first. Let's take this way. Okay. So I will take this del dot E is equal to 0. So how I write it? It's partial by partial x Ex plus partial by partial y Ey plus partial by partial z Ez. Okay, that's equal to 0. I am simply rewriting the Maxwell's equation and we will solve these. Okay, we will simply simplify these equations. Okay, so now tell me what this object is. So can I write this as, okay, anybody? So can I write this nebula perpendicular dot E perpendicular is equal to minus partial Ez by partial z? Can I write it? Can I write it? So what is this nebula perpendicular dot E perpendicular? Partial Ex by partial x, partial Ey by partial y. Can I write it? Everybody? Okay. So then it is minus partial Ez by partial z. Now we know the electric field has that kind of profile. Is it? So why I am separate? Because I know what is the profile along z direction. Is it? What is the dependence along z direction? That is that exponential of I k z minus omega t. Is it? So that is why I can remove this derivative along z direction. So now tell me what is the differentiation of this Ez with respect to z? So you need to differentiate this exponential with respect to z, is it? So what do you get? Huh? So look here, E is actually, okay, so anybody, if anybody is not following it, so this E is actually equal to E naught, okay, E raised for I k z minus omega t, is it? So what is Ez therefore? So Ez is having the same, let's say E0z. Let's assume this as a real, is it? So it is the Z component. What it will be? Kz minus omega t. So समझ आया? You got my point? Z profile will be like this thing. So that's why we are differentiating it. So let's write what is the differentiation of Ez. So it will be Ik. So it is minus Ik. So it will be simply Ez. Now you are having this as the first equation. So this is very important equation. So if you know the Z component of the E, you can solve this kind. So this is actually the homogeneous equation you see. Okay, so you will see actually the boundary condition which I can have in this kind of problem. So that will simplify this equation. Now let's say del dot B. Okay. So second equation. So what was the numbering? So let's call this as equation third. Okay. So let me check my. So I have called this as fourth. So this notation as third. So let's call this as fourth. I will keep my notation. Okay. So del dot B. Anybody can tell me what this del dot B is now? So it is the same thing. So like B perpendicular minus BZ by partial Z. How much is that? Or like this thing. B perpendicular. So it's equal to minus IK BZ. So it is this of the same form. Okay, so these are trivial equations. Okay, so now let's go to the another non-trivial equation. So another equation is, so you are having this curl of, okay, so the curl equation, so 4 and this is 5, huh? At least in this particular problem I will be using numbering, equation numbering, because we will see a large number of equations will arise. So another equation is this curl of E is equal to I omega by C B, is it? So now let's write it in the component form. Okay, let's write the curl of E. What it is? So let's write the x direction. What will be the curl of E? So partial by anybody? Partial by partial y E z minus partial by partial z E y. So this is the x component minus y component, then partial by partial z E x minus partial by partial x E z. Okay, then you are having z component, so it's partial E z. Okay, so it is E z, E z, E x, E x, E z. So then you are having partial E y by partial x minus partial E x by partial y. So what is that equal to? I omega by C. So this I can write x dx plus y dy plus z dz. Okay, I am not using ijk because I is actually iota here. So instead of getting confused, so we'll be using x, y, z. So now let's compare. I can compare the coefficients on both sides. Is it? Can I compare? So you compare the coefficients. What's your this thing? So I am having this. So comparing coefficients on both sides. So which implies coefficients of actually what? X, Y, Z. So what you get? Partial Ez by partial y minus partial Ey by partial z. That's equal to I omega by C dx. Then you are having partial Ex by partial z minus partial Ez by partial x. So I have actually taken this minus inside. So that's equal to I omega by C by. Then you are having partial Ey by partial x minus partial Ex by partial y. That's equal to I omega by C dz. Okay? So let's put it in the perpendicular notation, this transverse and longitudinal component notation. Is it true? Clear? Okay. So now let's look at this equation and this equation. Let's look at these two equations, okay? So while you are having partial by partial x here, is it? Acting on Ez. You are having partial by partial y acting on Ez. Is that true? So what I can do? Anybody? So if I write it in this, okay. So let me write like, okay. So minus x, okay. So let me form a unit vector. So minus, okay, let me form this kind of vector. Let's write I omega by c, okay, minus x by plus y bx, okay. So this kind of objective, okay. So what it will be? It will be plus x partial by partial x plus y partial by partial y, is it? And the other terms, okay. Let's look at how it will look like. So from these two equations, so how it will look like? Now tell me. So you will be getting minus x partial by partial z ex plus x partial. I am forming actually a vector, right? Okay. Then you are having plus y partial ez by partial y, okay, minus y partial ey by partial z. Is it true? Okay. So just look. So I will take these two objects first, okay? So what you are having? So x partial by partial x plus y partial by partial y. Can I write it in this fashion? Acting on Ez. Is that true? So then take these two terms. So you are having minus outside x partial by partial, okay? So like this thing, x, sorry, partial by partial z. So x ex plus y dy. Can I write it? Can I write it? So now if you see, this is actually a delta perpendicular, and if you see, it is E perpendicular. So that means you are having here, so gradient perpendicular acting on Ez minus partial by partial z acting on E perpendicular. Okay? Clear? So what I am trying to do, I am actually separating these equations, or I am rewriting Maxwell's equation in terms of the longitudinal components and the horizontal components. Clear? Sorry, longitudinal and the transverse components. Okay, so that's why I have figured out this kind of vector in this fashion. Is it? Clear? Samajh? Okay, we will see it in a moment what exactly this is. Everybody has written now? Huh? Okay. Okay, so these two equations are gone. Okay. So let me define my unit vector. So define a unit vector. A unit vector M. It is equal to 0, 0, 1. Is it a unit vector? So it's a vector along z direction, unit vector along z direction, is it? So can I write, okay, now let's write M cross B. Let's write M cross B. What is the cross product between M and B? You will see that's equal to actually minus x by plus y bz. Okay? So if you take the cross product, you will get this thing. Okay? So that means this object is what? M cross B. Okay, good. So therefore I am having one equation. Okay. Now look here. Okay. So therefore M I omega by C M cross B. Okay. So that's equal to this minus partial by partial Z E perpendicular. Clear? Clear? Okay. So now tell me what is differentiation of E perpendicular will be also having the same kind of this dependence, because it is Ex, Ey, is it? Both are having the same dependence. What will be differentiation with respect to Z? It will be Ik, is it? So that is equal to minus Ik E perpendicular. Clear? It's actually, if you see, it's actually taking the Fourier transform only in the one direction, only in the z direction. Okay? So that is the same kind of problem. We have done the Green's function in 2 plus 1 dimension Green's function. We took actually the Fourier transform only first along one direction, is it? Okay? So it's exactly the same thing we are doing here. So therefore I can write this very equation. Okay, so which implies I omega by C m cross B. Okay, so you are having plus I K E perpendicular, okay, plus this thing is equal to, so this is, now look here what you are having here. So transverse derivative and the transverse field, is it? So B is also the transverse field, is it? So that means these two equations represent, these are the two equations representing the transverse components, and this is actually representing the longitudinal component. Clear? So what is the numbering now here? Huh? So it will be 6. So now let's look at this very equation. Can anyone tell me what this equation will be? Anybody? Okay, so this equation I can write. Okay, that equation I can write. M. Can anyone tell me? So if you see, it's actually the cross product. Okay. So what is M? M is the, okay, so can I write it in this way? Cross of E perpendicular. Okay, that's equal to I omega by C E Z. Can I write it? What is M? Tell me. M is actually Z direction. So what is, I need to calculate what is the Z component of this thing. What will be the Z component? Like, what is Z component? No. Okay. So you are having I, J, K, is it? So partial by partial x, partial by partial y 0. And then you are having Ex, Ey, and 0, is it? Because, so this is what? Delta perpendicular and this is E perpendicular, is it? So what will be the K? So what is the Z component? So partial Ey by partial x, so that will be actually the Kth component. Minus partial Ex by partial y, is it? So is this the Z component? Is it? Okay, so that means, so you are, similarly, so you need to calculate the other. Similarly, from del cross B is equal to I minus I omega by C, I think E, is it? So you will get, so you need to check them. So there will be only change in sign here. So you will get I K E perpendicular minus I omega C m plus. So we have actually rewritten now the equations, so it's now easier to solve under given boundary condition. So let's call this as 8. Call this as equation 9. Okay. So these are the Maxwell's equations, separated with the longitudinal and transverse components. Clear? Clear? So longitudinal is separate and the transverse is separate here in this very equation. Now let's go to the what are the allowed modes. What are possible modes? First, which are actually trivial modes. So we call them as CAM modes. Okay? So it means transverse electric and magnetic. So TEM means transverse electric and magnetic. What does that mean? So what kind of modes they are? Okay, when I say you are having transverse modes, so so that means you allow only the transverse modes in your problem. Okay, so this is one of the conditions. So when you propagate a wave along a, let's say along this very tube, this conductor, okay, so you allow, let's assume only the transverse modes are surviving in the problem, is it? So what about the longitudinal modes? Those are actually Ez and Bz, is it? So if I am assuming only the transverse modes through the entire propagation they are surviving, what will happen to the, so in that case, so the longitudinal modes I assume to be 0, okay, so throughout the propagation. So this is one kind of mode, is it? So one kind of possibility is that, so in this case I use Ez is equal to 0 and Bz is equal to 0. So that means only the non-vanishing components of the electric field are what? The transverse components. Okay? So these are actually the trivial modes of this very problem. Okay, you will see it in a moment. So now let's get back to, let's look at, so this is our boundary condition, is it? Is it a condition? So it is some sort of boundary condition in our problem where you put only the z components to be equal to 0. Okay? So what are the, okay, let's look at the equation 4. Look at the equation 4. 4 and 7. From equations 4 and 7. So you are having this kind of thing. So 4 is this very objective. E perpendicular is equal to, so that, okay, tell me what is equation 4? So what is equation 4? So del perpendicular dot E perpendicular is equal to minus I K Ez, is it? So what is Ez? Ez is equal to 0. So this will be equal to 0. Samajh aa? Clear? So now let's look at the equation 7. What is that? No, one nation, just m dot. Okay, equation 7 is m dot. Okay, this object, is it? So what is that equal to? I omega by C Bz, is it? What is Bz? 0. Is that true? So if Bz is equal to 0, it implies therefore from that equation curl of this object is it's equal to 0. So this is from 4 and this is from 7. Clear? So look here, is this, so what it means? So curl of E, where is the curl of E? E perpendicular, these are the perpendicular components, is it? So what is the curl of E? Where is that very direction? That is the Z direction, is it? And you don't have anything in the Z direction. Clear? So from this very equation, you are having this curl of E, you are having actually magnetic field in the Z direction, is it? Because electromagnetic wave is moving in general, is it? But you assume you are having this object equal to 0. When you are having a curl of some field equal to 0, what does it mean? I can always express that field in terms of the gradient, is it? So this equation implies E perpendicular can be actually written as del phi, where phi is some potential defined on the surface of the conductor, is it? Since our waveguide is a hollow cylindrical conductor, is it? Clear? So substitute it back here. So what you will get? So you get like this thing minus nabla phi, that's equal to 0. So it is actually perpendicular in the, since it's E perpendicular, I need to calculate the gradient in the perpendicular direction, is it? So samajh aa? So it's this thing, so what that is equal to. So what this equation is? It is Laplace equation in the transverse direction. Okay? Clear? So that means, so this equation you need to solve the Laplace equation in transverse direction. So what it implies? Anybody can tell me? So it is in the transverse direction. Now look here, even though I have assumed no fields, no component of the field along z direction, is it? So along z direction you don't have any kind of component, is it? So you will see what it means. From this Laplace equation, what you get actually? What is on the surface of the conductor? So potential has to be constant, is it? So now let's take this very equation. So from this equation, can I write it like this in phi, nabla phi square phi is equal to 0? Can I write it? First tell me, everybody. just multiply it on one side 5. Can I get it? Okay, so now let's, so it's a two-dimensional thing. So let me integrate over the two-dimensional surface. What is the two-dimensional surface here? Here, it's xy plane. So let's integrate over dx dy. Okay. So let's calculate this very quantity and let's check what is phi in this very transverse plane. What exactly phi is? Okay. So can I? Okay. Now integrate by parts. So you integrate by parts. Okay. So what you get? So that will be simply equal to minus dx dy, this perpendicular phi dot because field vanishes at the boundary. So that's equal to 0. So, or in other words, I am getting this dx dy mod of this thing. So that's equal to 0. What it gives me? So this perpendicular phi is equal to 0. So which implies phi is constant. So when you are having gradient of phi equal to 0, what it means? Phi is constant. Now you are having phi constant. What E perpendicular is? Phi is constant. What will be E perpendicular? 0, is it? So which implies electric field is 0 actually. Which implies E is equal to, is it? So that means if you consider no longitudinal components of the field, it means you will be having no components of the transverse component. Similar, same kind of argument from the other, let's say equation 5 and 8. You are having del dot B equal to 0 and you are having a curl of B equal to 0. You will get the same Laplace equation and you will be having magnetic field equal to be 0. So that means you are having no magnetic and electric component. So that's why we call these transverse electric and magnetic modes to be trivial. So you don't have actually the propagation through the what? So when you don't have the components, longitudinal component and transverse component, what will happen to the wave? So it will not propagate, is it? So along these modes you don't have the propagation, is it? So samajh? Okay. So now let's consider the non-trivial modes. So bus.